Hello everyone, there's another Physics IB past paper review. This one is May 2018, standard level paper 1, and we're on page 13. So that's question 25, 26, 27. Okay, so 25 here we have a question about binding energy. We're told that the average binding energy per nucleon of an oxygen 15 nucleus is 7.5 mega electron volts. What is the total energy required to separate the nucleons of one nucleus of oxygen 15? Okay, well, we have to imagine what's going on inside the nucleus. We've got, let's do it down here. We're going to have, how many of these are going to have? Eight protons. 3, 4, 5, 6, 7, 8. 8 protons, which will all be experiencing a force of attraction towards each other from the strong nuclear force. But we'll also have 7 neutrons. 3, 4, 5, 6, 7. So the neutrons are going to feel an attraction to the neutrons, but the protons are also going to feel an attraction to a proton, but also the protons are going to feel an attraction to the neutrons. That's how these nucleuses can stay together. And so, of course, we're given the average per nucleon. So how many nucleons do we have? Well, 15. And so if we know the average of each of them, then to separate these out, if I was going to take one and pull it away, if I was going to take this neutron here and pull it away from the nucleus, I would need an awful lot of energy because it's held here by these bonds between neutrons and protons. Okay, so in fact, if we were to zoom in and just look at one of these, so if I was to zoom in and just look at this top section here, we would have a neutron and then a proton and a proton. There would be forces of attraction between all of them. Okay, force here and force here. They're bound together. And so for me to break that apart, I would have to overcome this energy. So I would have to separate all of these out, I'm going to have to overcome every single binding energy that there is between each of the 15 nucleons. So I can then say that I have to multiply my average binding energy by 15. So it's going to be 15 times the average binding energy, which gives me 112.5 MeV. And so if we round that up, we get C. Okay, so for question 26, we have a half-life question. And here we have, once again, with IB really likes to test ratios, and so here we have a ratio as part of our half-life. So let's take a peek at what's happening. Even before we do it, let's just remind ourselves, because I'm going to use logs to do this. There's probably other ways, but I think logs kind of helps just with the algebra. So we know that with half-lives, we have an amount of something, which is then equal to the original amount times this half to the power n. Okay, and then just as a side note, n is going to be equal to the time that has elapsed divided by the half-life of the sample. Okay, so to get this n down from its exponent position, we're going to use logarithms. Hopefully you can recall that all we need to do here, I'm just going to simplify it by saying we have n over no is equal to 0.5 to the n. So now we're going to bring the exponent down. So I'm going to say log of n over no is equal to the log, actually back it up, I'll put my n here now, my n times the log of 0.5. Okay, so when we can just log everything, and then that brings the n down. And so we're gonna use that in our solution here. Okay, so in the question, we have two pure samples, x and y. They have the initial same number of atoms, and the half-life of X is given as T half. Okay, that's nice and simple. Here's our ratio now. After a time equal to 4 half-lives of X, so this would be, let's put this here. This is now, whoops, I use my pen. This is going to be 4 T halves, right? We have a ratio, and the ratio is the number of atoms of X remaining over the number of atoms of Y being equal to 1/8. Okay, so let's write a statement about X. Okay, we're going to say the undecayed number of atoms in X is going to be equal to the original number of atoms in X multiplied by the half to the power of the half-lives, which in this case we're interested in are 4. Okay? And now we're going to put this into a ratio, because we're also going to say, let's do another statement, that the undecayed Y is equal to the original amount of Y multiplied by the 0.5 to this unknown value. Okay, and that's what we're going to try and find out. So here's where the ratio comes in. Remember that all we've done here is we've just put this as an equivalence. We've said the undecayed X, the number of the amount of atoms left after a certain time, is equal to the original and this equation, and then the same for Y. So what we're told here is that after a time equal to 4 half-lives, the number of atoms of X, this is going to be the number of remaining atoms. Okay, so what I'm going to do here is take this, oops, I should use the different color, let's go with blue. I'm going to take this and say that this is part of my equation. So I'm going to say NOx to the half 4, okay, is equal to the 1 part of my ratio over, so now over the number of atoms of Y, in other words, the undecayed amount of Y, which is equal to this. So this is going to come in here, NOY 0.5 to the unknown half-life, and this is equal to the ratio 1/8. Okay, so here's where I'm going to get my solution. This is my statement, and what's really important is now we can bring in the first statement in the question, which was to do with the same number of initial atoms. In other words, these two can cancel out. Okay, so that's quite convenient, isn't it? Okay, so let's now deal with the NY. We can say that the this unknown half-life value, this NY, remember, N is equal to time over the T half. And how much time has elapsed? Well, the time that has elapsed is 4 half-lives of X, right? That's what's given in the question, 4 half-lives of X. And this is over the T half value of Y. This is really what we're trying to find out. So we've just made another statement about what we're trying to find out. We can say that the T half value for Y is going to be equal to 4. So we make a bit more space here. I should have put that in. That was a mistake. Let's get rid of that completely. The statement that I'm just making now is 4t half of x over the n value here. Okay, so we're going to come back to this statement. We'll leave it here for now. This is going to be important in a minute. Let's carry on with this, and we'll simplify this and use some logarithms to get rid of, or to simplify it, and hopefully combine it with this to get our solution. So what are we going to do? Well, we've cancelled out these guys. They're gone. So now I'm just going to state that I'm going to say 0.5 to the ny is going to be equal to 8 of the 0.5 of the 4s. Okay, just simplifying it. And now I'm going to go and use my logarithms. I'm going to say log of the 0.5 multiplied by, I'm just going to put this in brackets here, ny. So the exponent here has come down. That's come down. And now here's a weird thing, because if you go ahead and do the sum, 8 multiplied by 0.5 to the power 4, well, you end up with 0.5, which is a bit weird, but that's just the way it is. But of course, this has to be logged as well, just to be consistent with the bringing of the exponent down with the log function. Okay, so let's keep going with our simplification. Now what we need to do is substitute this ny, this is our statement here, this is going to come in for ny, and then eventually we're going to solve here for this t half, and that should give us our solution. Okay, so let's go ahead, and I'm going to divide out my logs at the same time. So I'm going to say log 0.5 over log 0.5 is equal to this ny, which is equal to this. So 4t half of my x divided by the t half of my y is equal to log 0.5 over log 0.5, which happens to be equal to 1. So here I can write my solution. I can say that t half of the y, which is what I'm trying to solve for, is equal to 4 t halves of the x. In other words, what is the half-life of y? It's equal to 4 t halves of the x. So it's going to be d. Okay, so question 27, pretty easy one to finish up this page on. Energy level diagram for an atom has 4 energy states as shown in our Bohr model here, with typically energy increasing, going up. So it's asking, what is the number of different wavelengths in the emission spectrum of the atom? Well, if this is the energy going up, then the emission of the emission of EMR is going to come from when an electron drops down its energy state, or the atom can drop down its energy state. It doesn't matter what language we use. And so you're going to get an electron or an energy state dropping from one energy level to another. So we just have to count how many of these drops are possible. Okay, so if the energy is dropped from a high state to a low state, whether it's an electron or the energy state of the atom, it doesn't matter. If this happens, you're going to get EMR being produced. And so this is obviously one possible option. Let's go through and count all the other options. We're going to have this one, that's 2. This one, that's 3. Of course, it could just go to here, that's 4. It could go from here to here, that's 5. It could go from here to here, that's 6. Any others? I don't think so. So we've got 6 possible wavelengths of EMR that could be emitted from this model.